All right. Hello once again, everybody. Welcome to e-learning day 3 here for AP Calculus. Taking a look at our agenda today, Thursday, March 12th, we do have to finish up a little bit of loose ends from topic 8.2. Topic 8.2 is, if you recall, we're revisiting particle motion. We did a little bit of that in the first semester. It's been a while. The only difference now is that we can throw in the idea of the integral and see how that sort of interacts with these concepts. We did 2 very long examples, I know, on Tuesday's session. That was going to be probably one of the longest videos that you guys have throughout both of these weeks. Hopefully today won't be nearly as bad, but we're going to hit up the last 2 examples from section 2, which are very short. And then we'll see if you guys have any questions that you need clarified over the Skill Builder 8.2. It's a Big 10 activity. Remember, you can access all of these activities in the PDF form if you go to either my or Mr. Meunier's Schoology site. It's not imperative, I guess, that you print them out. You could just view them on the computer and do your work on a separate sheet of paper. Of course, you know, if you have the capabilities of printing them out, they're just a few pages and it kind of can help organize your work just a little bit. And then we will go ahead and just briefly introduce topic 8.3. And you guys, there's really nothing to introduce because we've already talked about topic 8.3 back in Unit 6. We're revisiting and reviewing our rate in and rate out. So we're actually already starting to review for the AP exam while we're in Unit 8, which is kind of nice. Okay. So with that in mind, let's go ahead and hit this. We've got the notes packet. Hopefully you have that somewhat handy. We're looking at the page 6, which is where example 3 begins. You know, if you didn't get a chance to look at the video or join us live from Tuesday, you might be a little bit lost because example 1 and 2 certainly fed into the concepts that we're going to talk about example 3 and 4. But I don't want you to stop. If you haven't watched that video, stay here. Just make sure that you do get a take a look at that. And if anybody's watching this recorded, if you haven't seen that video first, make sure you watch day 2 so that you can get the information from the example that we talked about with the space shot amusement park ride. And then prior to that, we had the problem dealing with just a particle moving along a line that involves technology. But what I wanted to do, I'm just going to briefly redirect you guys to page 5. We mentioned this on Tuesday. This page, Mr. Meunier and I can't probably convey enough to you how this information, how so important it is. And I know it's really intimidating. I know you kind of read through this table and I think there are 18 rows and it's all about a certain expression that you might see in a calculus problem and how you would translate that mathematically and what kind of calculus that you would perform to solve it. But to be honest, a lot of these rows make crystal clear sense and you probably know them already. For instance, if you look at the 3rd row down, a particle is at rest. Well, what does that mean? Well, that means that the velocity is 0. And I'm sure that you guys were probably pretty in tune to that. And I think we talked quite a bit about particle moving right and left just means that the velocity is either positive or negative. So many of these ideas you have already been introduced to from the first semester. Now, granted, there are a few new things, basically the things that might have an integral symbol. And you can now probably understand why we had to teach topic 1, average value of a function, first. Because if you look here at this row, the 6th row down, the average velocity of a particle on an interval AB, well, hopefully this looks familiar, right? It's the average value of a function, right? That 1 over b minus a thing out in front, and it's perfectly okay if we call it the 1 over b minus a thing. Just don't tell that to your college professors that Mr. Meunier and I said that was okay. But 1 over b minus a times the integral of whatever function you're trying to find the average of is always going to work, okay? And then, of course, if we integrate velocity, hopefully it makes sense to you that you do get position, right? You're just kind of moving up that ladder. Remember, we had position, position, velocity, acceleration as we take derivatives and move down. But if we start from acceleration and integrate and move up, we get the same kind of idea. Okay, so hopefully these ideas will make some sense to you. One of the bigger things that we're going to talk about in our examples today deal with the total distance that a particle travels, which you can see that's down here in this highlighted row. And this is something that's always going to show up on the AP exam. And we want to make sure that you get these two ideas straight, the thing highlighted in black and the thing highlighted in red, that the total distance traveled by a particle on the interval AB is integrating absolute value of the velocity. Whereas the displacement, in other words, what was this, the change in the position from the beginning to the end, is just the integration of the v of t without the absolute values. Because basically what happens is that if we put the absolute values in, that will take care of any situation where we might have changed direction. Displacement won't do that. And we felt like we had a pretty good illustration of that in our very first activity on Tuesday. It was going to be a cool activity where Mr. Mee and I would have actually stood up in front of your room and we would have moved back and forth, but we had to sort of kind of e-learning, kind of invoke that into the e-learning atmosphere and try to describe it a little bit more than physically do it. So again, I really would like for you guys to take a look at this table as much as you can. When you guys take the quiz next week, we're not going to be able to force your hand and say, hey, you can't use your notes. Of course, you're going to be able to use your notes, and this might be really handy for that. All right, and we're probably going to be referring to it a little bit as we do our problems here today. So with that said, let's go ahead and take a look at example 3, which is actually a pair of multiple choice questions. All right, and they're very conceptual, so there's no computation that has to be done with these. So if we read multiple choice question 1, it says a particle moves in a straight line with velocity v of t meters per second, where t is time in seconds. At time 5, the particle's distance from the starting point was 6 meters. What is the total distance the particle has traveled between 5 and 10? And I would like you guys to think about this just a little bit. You don't want to give too much away. You've got 4 choices. And if you're comfortable enough, and I know that this is tough to do, guys. This is you're out there because your name is attached to this, but if you're comfortable enough, why don't you give it a shot and put your answer in the chat? Is it A, B, C, or D? What is the total distance the particle has traveled? And we really appreciate those of you definitely going out on a limb here to do this. But okay, lots of great answers, lots of great answers. Let's go ahead and reveal the answer is C. The answer is going to be C. We see that C is the absolute value of v of t being integrated, and it seems like it's being done between the 2 times that we want. And we kind of connect the idea that total distance is definitely connected to integration. Now, I'm so glad nobody chose A, and A is probably the worst possible answer in this mix. But I would like to talk about all of these 3 that aren't correct. They do stand for something. They mean something. And it's really worth our time just really quickly to talk about that. So if you look at A and you kind of formulate a thought here, and I don't want anybody to type this in because it's going to take a lot of typing, but I just want to pause for about 10 or 15 seconds, and I want you to think about, if you had to put into words, what does choice A mean? 6 plus v of 5. Think about what you would say, but you don't have to type it. All right, hopefully nobody fell asleep there, right? To be honest, A is just really the velocity of the particle at time 5, but just increased by 6. for whatever reason. I don't know what kind of context that would ever happen, but we're kind of tricking the students to understand that the absence of the integral is a very egregious thing, okay? Now, we want you to know that you don't have to write that down, but I believe that the solution key to the notes are now posted on our Schoology. If they're not posted in both of our sites, they will be very soon. We only have them up to about topic 5, which is going to be fine. We're going to expand on those, and then hopefully by the end of next week they'll all be completed. But that way you guys can go back and look at the solutions in case you may have missed something during the videos. Real quickly for B, we'll talk about this one together. B is pretty darn close. B is actually a pretty good wrong answer, I suppose. But the problem is that we don't have the precise absolute values around V of t. And here's a really cool way that you can think about this. If we integrate V, don't we get position, right? The integration of velocity is position. And if we use the fundamental theorem of calculus, then really B is just the position at time 10 minus the position at time 5. So there's been like a displacement. You know, how far apart are those two positions? And then we add 6, and if you think about what 6 is, I believe that 6 is the position at time 5. Is that what you think is going on here? At time 5, the particle's distance from the starting point is 6. So I think it's definitely safe to say that the 6 is really the position at time 5, which now brings up an interesting situation. What does all this simplify to? Well, again, you don't have to type that in the chat because I think it's pretty clear. It's just the position at time 10. So if you had to interpret what B means, all it is just how far away from the starting point we are at time 10. Notice that that's not the same thing as the distance we've traveled from the starting point, nor is it the distance that we've traveled between times 5 and 10. Okay, and then if you look at D, we've already talked about D when we discussed B. It's just the difference in those positions again, right? From time 10 to time 5 without adding 6 to it. Okay, I'm a firm believer, and Mr. Meunier I know agrees, that if you guys can look at some of these wrong answer choices and understand why they're wrong, it really will help you with these conceptual questions. Okay, right. We have one more multiple choice question with example 3, and then we'll move on. This one, it says, a particle moves in a straight line with velocity v of t given by this quadratic equation, t squared minus 3t minus 7 meters per second, where t is in time in seconds. T is time in seconds. Probably ought to get rid of that in, shouldn't I? At time t equal 2, the particle's distance from the starting point was 10 meters in the positive direction. What is the particle's displacement between time 2 and time 9? So we would like to give you a moment to think about it. Don't type anything just yet. That way people can still think about it a little bit. Is this choice A, B, C, or D? The particle's displacement between time 2 and 9. And let's go ahead and open up the chat for you guys to fill in what answer you think it is, A, B, C, or D. Some good answers. All right. It seems like our answers are confined to A and B, which is a good thing, you guys. I was so hoping that nobody would go to C or D. And the reason is because with absolute values around the V, that gets us into the idea of distance, right? In fact, C is the distance traveled from time 2 to time 9. And D is just the distance traveled from time 2 to time 9, but we can add 9 more to that for whatever reason. it really doesn't matter. Now, the big difference between A and B, of course, is this plus 10 that's tossed into choice A. And if we read, whoops, sorry guys, if we read the problem really carefully, it says, what is the particle's displacement between time 2, and time 9. Just by that alone, we can go with B. But I want to talk about A because A's got a really neat thing going for it. And A would have been a really good answer if there was just one different tweak to this. And if I said, what is the particle's, I guess, distance from the starting point, or I guess I would say the particle's displacement from time 0 to time 9, I guess I would say. See, by adding that 10, we're including the fact that at the beginning of this interval, when time was 2, the problem says that the particle is already at 10 meters from the starting point. Okay. Notice our question didn't really say anything about that issue. We don't really care what happened prior to time 2. It's only what's going on between time 2 and time 9. Okay, so hopefully that makes sense a little bit. I know it's a little tricky, but we've got some problems that I think will help in that Big Ten activity. And I think example 4, which is a really interesting question. I don't think you guys have ever done anything like this before, will help address some of those issues, okay? For example 4, we're going to use the N.U.T strategy to interpret motion. And let's review really quickly what N.U.T means. We had to talk about N.U.T, I think, during one of our videos earlier this week. But N.U.T is the way that you would justify or explain what a derivative or an integral means. And the N stands for noun/number. Basically, it's the answer to your problem plus all of the important context around it, like what that particular number is signifying. The U stands for units. You always have to put your correct labels on both the number that you got and the time. And T is, as I just said a moment ago, is time. And a lot of times it's the T that will force kids to not earn the point on the AP exam. So we want to make sure that we do a good job with that. And this particular chart, as you can see, just scaffolds those 3 things into 3 columns, and we have to fill in the missing details. So let's read the directions. It says the position of a particle moving on the x-axis in feet from the origin is given by x of t. The velocity of the particle in feet per second is given by v of t, no surprises. The acceleration is given by a of t. For each of the integral expressions given in the following table, interpret its meaning by filling in the missing noun, appropriate units, and/or the correct time value or interval. So we start right off with the first one, x of t plus the definite integral from 2 to 4 of x prime of t. And at least we know one thing. At the very end, this problem is specifically talking about something that's happening at a specific moment, at t = 4 seconds, which might be surprising to you because typically an integral is defined using a word like from and to. So there must be something that's going on with this problem. Well, what's happening, and I'm going to use a little space below here if that's okay. We have x of t, of course, or x of 2 hanging around, which is just the position at time 2. But if you think about what would happen if we integrated x prime? Well, the integral of x prime would give us x, right? The prime just goes away. And because we have boundaries, we're looking at the fundamental theorem of calculus, right? So we would subtract those results. And before you know it, you notice a couple of things canceling away. So all that we have in this problem is just x of 4. So we have to think that x stands for position. And I don't want anybody to get confused because I know we used s for position earlier. They're sort of interchangeable. My experience with the AP exam is that x is used a lot more often because we typically move side to side on the AP exam. Physics, those of you that might be taking an AP physics test, you might be dealing with motion that moves in other directions that is affected by gravity, but the calculus exam will not be like that. So basically, this is just x of 4, which is just simply the position of the particle, right? So that's what we're going to do. We're going to go ahead and fill that in. as our noun. So the position of the particle. Now notice we can't say what that position is. This problem did not give us numerical values. So when I say that N stands for noun/number, in this example, it really only stands for the noun. And then the units, well, what would our units be? Well, our units up here are designated as feet, and we always kind of measure them from a home base, so to speak, and that home base would be from the origin. So those are your units in feet from the origin. And then, of course, the time is at t = 4 seconds. Notice we put the seconds in there, so we have the units. And that's kind of what's going on. If you look down here at the bottom of the screen, x of 4, it's neat to see how this integral sort of disappeared on us, and it wasn't an interval of time anymore. It was a specific moment of time. Okay? So hopefully we'll be able to go through the rest of these a little bit more efficiently. So if you look at number 2 here, integrate x prime from 1 to 4. Well, again, you can think about, well, gosh, integrating x prime just gives us x, right? And we'll evaluate this from the top boundary of 4 and subtract the bottom boundary of 1. So now we have a difference in positions. All right, so you could think of that as a change in position. There are probably other ways that you could describe it. The difference in the position would be one, but I like the word change in. We've used that quite a bit throughout the year. So this is certainly the change in position of the particle. What would you think the units would be? This one's kind of tricky. The units would be, get right, red pen going here, in feet. But I'm going to stop there. And I know that's a little frustrating. Why do I stop there? Well, we don't really care about the origin here, if that makes any sense. If you think back to the previous example, it reminds me a lot about why we chose B and not chose A, because we didn't really care about how much we had moved prior to that particular beginning time interval. Okay? So you're just talking about what's happening in between time 1 and time 4. We've had a change in position, it's measured in feet, and then do you think that this would be a problem that we would use the word at, or the phrases or words from and to? Because we are talking about an integral with an interval, right? So we want to use from t = 1 to t = 4 seconds. Okay. And I know some of you might look at this chart and think, oh my gosh, this is so boring, but it's amazing how impactful this thing is. This is such a good skill to kind of practice with. Okay, let's take a look at the third one down. Now, for this one, I just want to do something just temporarily. If I got rid of the 1 over 4 minus 1, I'm hoping that we're all over this one, right? If you integrate absolute value of velocity, that should tell us distance, right? Total distance traveled. And that's exactly what we've got right there. But when we toss in the 1 over 4 minus 1 in front, our hope is that you kind of link this to the beginning lesson, the one that we went through on Monday, and see that this, or actually even last Friday, we want you to think about this as being the average value of that function, right? Because we have the 1 over b minus a. Okay, so this is the average value of, what is this called again? And we see that that is distance, but we're going to have to think about this just a little different, you guys. And I know that this is where things get kind of frustrating. Absolute value of v is also a very important idea if we go back to the chart. Absolute value of V. Let's see, where did we see absolute value of V? Anybody see absolute value of V? Right here it is, right? Highlighting that there. And it's the speed of the particle is the absolute value of the velocity. So if we return to our chart, we need to think about whenever you have the 1 over b minus a, it's changing things just a little bit. We don't really want to talk about distance here. We're going to talk about the average of the speed. And that's what we've got. This would represent the average speed of the particle. And of course, our units are in feet per second. And then our time we have to think about, is this talking about a specific moment or is this a from to interval? And when you think about average, that kind of indicates that you're looking at like an interval of time and figuring out, on average, how fast was this thing going? So that idea of the interval of time is going to cause this to be a from and to. I think that this is definitely one of the trickier ones because it's so common that a student wants to start looking at total distance. But that's not going to come into play here because of that 1 over 4 minus 1 sort of overrides that idea of distance. Okay. Let's take a look at number 4. Number 4, I actually had a little bit of trouble with when I first saw it, and I was making it too difficult. Let's attack number 4 really the same way that we attacked number 1. In fact, don't they look very similar? The only difference here is that we seem to integrate V instead of up here integrating x prime, the derivative of position. But wait a minute, isn't the derivative of position the same as velocity? So really, this one can be rewritten as that x of 4 plus, and then if I integrate velocity, I get position, but this time the boundaries are just a little bit written differently, right? It's odd, but the lower number is written above and the higher number is written below, but that's fine. We still subtract them, top minus bottom. And this time we see that the x of 4's cancel. So this is going to be the position of the particle at time 2, right? So it's a very similar answer to the first row. The position of the particle. And if you haven't figured it out by now, but the position is always going to be measured in feet from the origin. And then our time is a specific number, and it's at t equal 2. At t equal 2 seconds. Okay. I bet you guys are all over the 5th row here. The integration of the absolute value of v of t from 1 to 4, right? In one word, we can probably see that that is distance, right? We don't have that 1 over 4 minus 1 in front, so we can just rely on our normal definition of distance. So it's kind of nice if you tidied up that word distance and maybe put the word total in front of it. I think that's a very strong way to present that. So we can say that the total distance the particle traveled. Oops. The particle traveled. I noticed that my bandwidth here is kind of dwindling. You can tell because the pen, the writing is getting a little bit tougher, but I've got 3 people in my house other than me that's online right now. So, okay, the units here, the total distance that we traveled would certainly be measured in feet. Now, why not in feet from the origin? Well, we don't really care, once again, where we were at the beginning, okay? When you talk about position and distance in these two contexts, I guess I should be careful with that. When we talk about the total distance traveled, all we care, again, is what's happening between 1 and 4, okay? So we only want the words in feet here. And then the time interval is definitely from time 1 to time 4 seconds, okay? Now, if you look at the last one, they went ahead and gave us the noun for it, which it's nice that they said it's an average, right? It's the average value of a function. It has that 1 over b minus a look to it. And the function that we're averaging is the a of t, which is acceleration. So we have the average acceleration of the particle. Now, what would acceleration's units be? That's a little different here. Acceleration would be measured in feet per second, or we could say in feet per second squared. So we have to be kind of careful how acceleration has that extra factor of time in its denominator. And would you say that this would be at a specific moment in time, or is it over an interval? Well, again, it's got that word average, so that's definitely an interval. So we're using t equal 1 to 4 again. All right. And that pretty much wraps up all of section 8.2, you guys. The notes you can see just go right into section 3. Now, what I'm going to do here is, I know that originally in the, I'll bring it up here, in our agenda, we said that we would take some questions over 8.2 Skill Builder. What I'm going to do is I'm going to jump and do the example 1 really quickly from 8.3. At that point, you've kind of met your obligation. If you feel like you don't have questions or any issues with 8.2, you can go ahead and leave the Zoom session, or if you are watching recorded, you can stop right there. But if you do have trouble with that skill builder and you want to make sure that you're getting comfortable with it, you might want to stay tuned in. It's probably a good idea to let you know that Mr. Meunier has written a quiz that covers 8.1 and 8.2, and you guys are taking that Monday, right? I think we have a deadline for Monday night. It's a 5 multiple choice question, so it really looks like the normal quiz that you would take in class. The only difference is that you would take it through Schoology, okay? And we'll talk a little bit more about the format of the quiz in tomorrow's session, but just kind of put that on the horizon that you will have quizzes still. I think we're going to have one at the beginning next week and then one at the end of next week that covers the area between curves lesson that we'll talk about Monday, Tuesday, and probably even a little Thursday. Okay, so we're not completely off the hook, right? We do have some assessments that we have to give. And we're going to be pretty hardcore. If a student does not take the assessment, of course you would get a 0, but that 0 is something that you could not drop with your Khan Academy incentive, right? We don't want to award kids for taking a 2-week vacation during Coronapocalypse, okay? So keep that in mind, all right? The quiz isn't terrible. You guys, if you work on the skill builders, take some questions, you're going to be in good shape, okay? But I want to make sure that for those of you that are understanding this, that you're not kind of having to hang around for any longer than you have to, okay? So let's go ahead and move to 8.3. This is an old AP question, as you can see, from the year 2010, and it's one of our rate in and rate out, and that's what you can kind of see here. If you read the topic title, it says using accumulation functions and definite integrals in applied context. This is almost word for word the same lesson that we had back about midway through Unit 6. And we kind of call these rate in, rate out. Basically, you get some information about the rate of change of something coming into the process, and then there's a rate that's kind of leaving the process, okay? Now, in addition to those ideas, this problem here is full of a lot of other very cool things as well. So, other cool things that relate to the beginning part of the year. So it's a good review question, and this is really what we're doing right now. We're starting to review for your AP exam. So here we've got a zoo that sponsors a one-day contest to name a new baby elephant. Zoo visitors deposited entries into a special box between noon and 8 p.m. The number of entries in the box T hours after noon is modeled by a differentiable function E between 0 and 8. The value of E of T in hundreds of entries at various times T are shown in the table above. So you can analyze that table and kind of see this is sort of on a running accumulation of how many names have been placed on pieces of paper and thrown into that ballot box. All right. And so at the end of the 8-hour period, it looks like there are 2,300 names. So in part A, it asks us to use the data in the table to approximate the rate in hundreds of entries per hour at which entries were being deposited at time t equals 6 and show the computations. Now, this is a calculator-assisted question, but that doesn't mean that we need the calculator for every single part. So we'll kind of make those decisions on the fly. Now, for a problem like this, we've taken you here before many times. In fact, one of the very first questions that we even did with you at the very beginning of the year, way back in July, was this very thing, taking the derivative of a table. So if we're approximating the rate at which entries are deposited, then notationally, that's the derivative of E, right? And we're wanting to do so exactly at time 6. So now the question is, well, how do you take the derivative of a table? Well, the only way to do that is to have a little cooperation, and that would be to have a pair of numbers that are on either side of 6, equidistant away preferably, so that you can just use your regular slope attack, right? Because that's what a derivative really is. It is the slope. Now, this is an approximation, so we should put an approximately symbol there. It's probably not likely that you would be counted off for that, but we would really like for you to understand the difference between equals and approximately. It makes you look good on paper. All right, so in this particular case, we're going to take whatever E of 7 is and subtract E of 5, and we will divide that by 7 minus 5. And on the AP exam, you would have received a point for writing that down. Now, the next point would be to actually compute the answer, and that would be to fill in the values 21 minus 13 over 7 minus 5, or if you want to go ahead and simplify that to 2, and that would be acceptable if you wanted to leave it there because you don't have to simplify. Now, if you do simplify, I believe that the numerator is 8, the denominator 2 would give you 4. The only thing that we need now is a label, and the label is sort of it's possible that if you didn't put the label, you would be exonerated, you'd be off the hook, because it did say what the label should be, hundreds of entries per hour, but I would like to go ahead and write that out. We'll just basically copy that word for word, hundreds of entries per hour. This is a funny story here, guys. A lot of my students will ask about how much you can abbreviate on the AP exam, and it's actually pretty lenient. I was not a reader back in 2010, but I remember having a conversation with somebody who was, and he had said that he graded many AP exams where a student had abbreviated hundreds of entries as hose. So he kept seeing hose per hour or hose all over the test, and it was perfectly acceptable. So, all right, let's take a look at part B. Use a trapezoidal sum with the 4 subintervals given by the table to approximate the value of 1/8 times the integration from 0 to 8 of E of t with respect to t. Use correct units. Explain the meaning of that integral in terms of the number of entries. Now, this problem, you've got sort of 2 things that you have to battle. We have to review the trapezoid sum, which I'm sure you guys are like, what's the trapezoid thing again? We'll go through that. And then we also have to understand that this 1/8 is something a little bit more significant, right? Do you recognize this as that 1/b minus a thing? right? So this is an average value of a function. It's the average value of the function called E, which is the hundreds of entries. So we could put those ideas together, and this is actually the average number of entries. All right, and when we get to the end of the problem and explain the meaning, we're going to definitely use those words. But prior to that, let's go ahead and review our trapezoid rule just really quickly. And what I will do is I'm going to try to model really good notation, you guys. So I'm going to write that integral expression with the 1/8 in front. And because this is an approximation, I will use approximately symbols. I'm going to plop that 1/8 down so I don't forget it. And then I'm going to put a bracket or a parenthesis, whatever you choose, and then let's start the trapezoid rule. Remember the formula for the area of a trapezoid. I'm going to write that up above here to the right. Area of a trapezoid is 1/2 times the sum of the bases times the height, correct? And we just have to remember that the height, whoops, let's see if we can fix that. The height, once again, is just really the gaps in between each of these intervals. So from 0 to 2, we have 2. From 2 to 5, there's 3. You can tell that the h is not consistent. It's kind of all over the place, right? So along the t-axis is the height of your trapezoid, and then the vertical axis, which would be the e-axis in this case, we would have these vertical segments, if you can picture what the graph might look like, that go up to 0 and they go up to 4 and 13, etc. So the pairs of those serve as your base 1 and base 2. So what that would mean is for our first trapezoid, we would take 1/2, multiply by the sum of the two bases, which would be 0 and 4 for that guy, the first two numbers in the bottom row, and then multiplied by the h that we have on top 2. And then one trapezoid down, 4 more to go. And once you understand how one of them is put together, the rest of them pretty much fall into place. Now, for trapezoid number 2, we have to use the 4 and the 13. Notice how the 4 gets used twice. He's the base of 2 different trapezoids, one to his left, one to his right. And then his height would be 3. And then we just keep doing that for the next trapezoid. Height of 2, and then the final trapezoid. Bases are 21 and 23, and a height of 1. Okay. We will have more reviews with the trapezoid approximation as we get closer to the AP exam, but we just want to keep it on your radar. That's the whole point of this with the Riemann sums, is to keep them on the radar. Now, this is a calculator-assisted question, so I'm not going to type this in a calculator because I know that you guys can enter something like this. You're not going to have any trouble. So let's say that we push all of our buttons that we need to push, and we end up getting 171 all over 2. That's what it turns out to be, you guys. Okay, with that 1/8 still in front, which means that we end up with 171 over 16. Okay, if we choose to write this as a decimal, it's perfectly acceptable. That would be 10.688, right, if we type that in. But now we have to state, using correct units, what does this integral mean in terms of the number of entries? Okay, I'm going to write this in purple. So we've already said that this 1/8 means that we're going to have average. So we can just start it off by saying the average, and you can totally abbreviate, guys, the average number of entries. You've got your noun right there, I think, the average number of entries in the box. I don't think the phrase "in the box" is required. It does give it a little bit more color. But we do need to put our time. And we also need to put our units. So for our 10.688, I'm going to put that number at the end. Doesn't matter what order you write the numbers in, so I'll give you a little bit of options and variation when we finish this. But we do need our time. So the time would be from time what? 0 to 8. So we'll say, oh, there's so many ways to do this, guys. You want to say from t equals 0 hours to 8 hours. That's perfectly fine. If you wanted to make it look even more impressive, what does time 0 mean? What time of the day is time 0? Noon, right? So you could say from noon to, and then time 8 is 8 p.m. Now you don't have to do that. If you just generically said time 0 hours to time 8 hours, it would be acceptable. And then we need to put our answer. Now, the way that you put this answer is really, I know this seems crazy. What is this, 10.688 hundreds of entries? Okay, I'm going to write that. I'm going to write that because it's safe and I know it's acceptable. As long as I get that unit in there. But for those of you thinking, boy, that's just a really stupid way to communicate something, could you just move the decimal place over a couple of places and call this 1,068? How can you really have an eighth of an entry? You know, maybe somebody was writing the name of the elephant and the paper ripped or something. I don't know. I would say when I looked at the scoring rubric of this, if a student called this 1,068 entries, they did receive credit, even if they rounded it. I don't like to advocate rounding to my students if the question doesn't say specifically to round. So that's kind of the reason why I like to go with this, even though it sounds absolutely ludicrous. Okay, so hopefully that's making sense. You guys doing okay? Guys, we're almost done. Got a part C and a D here, and we'll wrap up here. So at part C, it says at 8 p.m., volunteers begin processing these entries. They process the entries at a rate modeled by the function P, where P of T is given by this cubic equation. And they're going to do these processing from time 8 to time 12. So notice they wait until all of the entries are in the box, right? Time 8 is when the box closes. And then from like 8 p.m. to midnight, they're going to like figure out, what are we going to name this elephant by counting up all the names? So according to this model, how many entries had not yet been processed by midnight? Had not yet been processed by midnight. Well, what we're going to do here is we have to think about the total number that are being processed. Okay, so I might start with that if that's okay. So if I know that P of T is the rate at which we are processing, to get the total number that I've processed, we would just simply need to integrate that rate. And it's perfectly acceptable on the AP exam or on Mr. Meunier and I's exams to just integrate the name of the function P of T. You don't have to spell out or write out all of this expression. It's already listed in the problem. And we're going to do this over the time interval 8 to 12, right? And that will tell us the total number of entries that have been processed. But the question wants to know how many entries had not yet been processed. So what we have to do is figure out, well, how many were sitting in the box to begin with? Do you all see how many there were when we started to count? It's this number right here, right? 23 or 2,300. We can just use 23 in this case because this is going to be measured in hundreds. So that 23 starts this expression, and then we subtract the total amount that we did process. Hopefully that makes sense to you. Okay. Now, this is a calculator-assisted question, so you would not have to integrate this by hand. It's not difficult to do, but plugging the 12 and the 8 in might be a little cumbersome. And for the calculator things that we do that are fairly easy, I'm going to not demonstrate them. But if anybody needed to see what this looked like after the video when we start going into our Q&A, I would be happy to kind of talk you through it. But basically just type this thing in and integrate it. I don't even know if you need to define this function, because you're almost at the end of the problem, and I don't think that you're going to be using it all that much. So if we go ahead and just trust your teacher here that I've entered that into the calculator, and it actually is a very nice answer. It's 16. And if we do subtract these, we get, of course, 7. And then we have to make sure that we either say 700 entries or we say 700 entries to get that label on there. Okay? Last part. According to the model from part C, at what time were the entries being processed most quickly? And you know what? Now that I think about it, I think I told you a lie. We probably would have benefited from defining this P of T in our calculator. So, whoops, I'm going to probably show you that after all here in part D. So according to the model, at what time were the entries being processed most quickly? What I want you guys to be able to extrude from this is that most quickly means maximum. We want to find a maximum of at what time were entries being processed. So the entries being processed is modeled by the function P of T. So we're going to maximize P of T. Notice that this is on an interval 8 to 12. So that means that this is an absolute maximum problem. So what does that mean? That means you have to find your candidates, right? And you put together your little T-chart, and then you just go from your chart by finding out which value of P is the largest, okay? Now this problem won't be as bad because we have the calculator that we can use. So the very first thing that we want to do is we have to figure out, when does P prime of T equal 0? That's our first goal, okay? So to do that, we are going to use the calculator. So I'm going to drag in the Inspire here, and it's up to you. If you have your calculator handy and you want to follow along with me, you're certainly welcome to. It's probably a good idea, but if you don't have your calculator, you can at least kind of tune in and see what I'm doing. So I'm going to go ahead and define that P of T because we're going to use it several times. So you hit your P of T, doesn't matter if P is capitalized or not. And then control math template does your colon equal, right? Oh, that's funny. Make sure the colon equal comes after the parenthesis. I actually hit my mouse pad and it changed it. So P of T colon equal, and then we'll enter that function, which is T cubed. And boy, if I enter this wrong, make sure somebody says something in the chat. Minus 30T squared plus 298T minus 976. Okay, so if we hit enter, that should say done. And then the next thing that we want to do is take the derivative of this and set it equal to 0. Well, I know that the derivative of this is pretty easy to do, but I've got a calculator, right? I've got a calculator that computes derivatives. So I'm going to go ahead and go into the menu option and use algebra. And let's tell this thing to solve the derivative of this P of T. Shortcut for derivative is shift minus. Make sure that you take your derivative with respect to T of course, the function P of T. Notice how it's bold. The calculator understands it. And we're going to set that derivative equal to 0. And again, solve for T, so we have to put comma T. Now, it's possible that we could get a lot of crazy answers here. The only answers that we care about are what are between 8 and 12. Okay, so I'm going to go ahead and hit enter just to see what I've got. Okay, not too bad, not too many crazy answers. I don't like the fact that they're written in non-decimal form, but that's our calculator showing off. So of course you guys could just hit control enter and it's going to convert them, right? I think most of you know this, but if you don't want to go through that process, remember when we were typing this in, if you had just placed a decimal point after any number in the entry, which really you only have one option, there's only one number, the 0, it'll automatically give you those decimals, okay? If by some chance you had a situation where there were so many of these and you had to scroll over, there's another way that you can isolate the answers to be between 8 and 12, and that's something that we can certainly talk about in class. So those are the two critical values. So let's write those down so we don't lose track of them. So P of t we know is equal to 0 when t is approximately 9.1835. I'm going to go to 4 decimal places just so that I have really good accuracy for my final answer. And then I have to remember that I have to test the endpoints as well, right? The endpoints, which are 8 and 12, right? The time that we're doing our processing, could also play a role in figuring out at what rate we're processing the fastest. So now you just set up your table. You would allow the left side column to be your times, and the right side will be your P of t's. And we can list those times. It does not make any difference if you list them in numerical order. I always like to do that, but as long as they're all in there, you'll get credit. And like I said, we have the calculator to use, which is going to make this go much, much faster for us. Okay, so we grab the calculator one more time, and then we just basically figure out, well, what are all of these values? What is P evaluated at 8? Well, there's our answer. Interesting. P of 8 is 0, which means right when we start to process, we're not processing very quickly. Basically, the people have just sat down, they've started to empty the boxes, but we haven't really written down any elephant names yet. So I doubt that that's going to be our answer. That's not working very quickly. So if we go to our next value, 9.1835, right? That gives us a decimal. Okay, we'll record that in a moment. How about our next one, 10.8165? Ooh, not nearly as good as the P of 9.1835. And then finally, the end time, midnight, right, when we're getting ready to wrap up, we were still processing and we were working pretty good right before we stopped. And it turns out that's our answer. So you see that if we did not check the endpoints, we could have been in big trouble. So for your answer here, to really be able to receive full credit, you guys, you would have to fill in these P of t's. Now, we would understand that you used the calculator to do this, and you're showing us evidence by filling in the table. I could go to 3 places at this point, guys. It really doesn't matter. Okay, I think those were my results, weren't they? 089 and 911, yeah, if I round. And so we see that our biggest answer is this 8, so we'll finish this up by saying the entries are being processed most quickly, I guess, yeah. And you could say at time 12, right? At time t equal 12 hours, or you could just simply say at midnight, right? Either way is fine. But I don't think the problem says you had to tell me the rate at which they're being processed, right? It only asked you at what time. If it asked you at what rate are they being processed most quickly, you would have to say 8, and the units would be 100 entries per hour. Okay. All right, I know this took us right up to about an hour, so we definitely appreciate you guys hanging around. And we also want to invite you, if you are feeling up to it, we have the skill builder. I'm going to slide that over here, and I was going to just stay on for a little bit. If anybody had any questions with this, remember that you do have a quiz that's coming up on Monday, and we also can use a little bit of time in our session tomorrow. I'm going to try to make Fridays shorter, but a lot of it just depends, because Friday is supposed to be a short day for you anyway, right? We try not to use any more of your time than what we would already be using on a school day. But this one I know went a little long as well. So again, feel free to take off if you want to, and if you want to stick around, we'll take some questions over this. So, all right. Yes, for those of you doing the IUPUI math contest, I will be back at school in the ALC parking lot tonight from 6 p.m. to 6:15 p.m. so that you can drop off your submissions, and that would certainly go to any of Mr. Meunier's students as well, and I'll get those mailed for you. And again, if anybody has a submission, even if it's just one problem, it's worth my effort to meet you, find you, whatever it takes, and I'll get that mailed for you. I know I have a few people that could not meet me at those times, so I've had people actually drop them off at my door here at my house. I've had one person put it in my mailbox, and I've got a few that said, hey, they have a really good scanner at home and they're going to scan it and send it to me, but I'll definitely be around if you guys need help with that. Okay. How are you guys doing with this skill builder? Does anybody have any questions yet? I understand that you also might be spending a lot of time today and maybe early tomorrow working on it. And for that matter, you guys are more than welcome to keep working on this through the weekend. That's perfectly fine. Hopefully your attention will start to turn to getting ready for the quiz. 8.3 has no homework. So the rate in and rate out lesson that we're doing, there is no homework assignment for that. Yep, let's help set up part A, not a problem. So it says in part A particle is moving along the x-axis for time greater than or equal to 0. The position is given by x of t being this cubic. At what time t does the particle change directions? And I think you want to work this skill builder with the mindset that it is no calculator, right? Do any of the problems have a calculator icon next to them? If they don't, then you really want to try to do it without. I don't think any of these really require a calculator. My friend who wrote this, I think, had mentioned that to me. Now, obviously, if you have to use the calculator to make sure you understand something or you want to check something, you're not cheating if you do that. But we just want to make sure that you know, like going into like the exam, a lot of these questions could be done without a calculator. On our quiz that we're giving you on Monday, we can't stop you from using a calculator, and we get that. But just kind of keep in mind the big picture. You want to be able to do these without. So particle changes directions. So if we remember particle change directions, if you're okay, I'm going to bring up the notes here really quickly. I'm going to go back in time and go to this table and talk about particle changing directions. Well, I don't know if that's necessarily, oh, I lied. It's right here. It's way down the bottom. So what does it mean for a particle to change direction? And it says this occurs where the velocity of the particle changes from positive to negative or negative to positive. So if we go back to the problem, we need to figure out, first of all, what is the velocity? Okay, well, the velocity is just simply the derivative of position. Okay, well, that's not too bad. So we'll take this derivative, 3t squared minus 18t minus 21. And then we have to think about where this changes position. Okay, we change position, first of all, whenever we potentially could equal 0, right? Because the only way that we can change signs is by doing it at 0. That's that whole intermediate value theorem that was introduced at the beginning of the year. Now, I'm hoping that this is a pretty friendly equation that we can solve. So we look and we say, oh, I think there is a factor that can come out. So we can bring out a 3. And if we factor out the 3, the 18 would turn into a 6, the 21 into a 7. And now you just have to dust off some Algebra 1 skills, which I know sometimes is a lot easier said than done. We are sympathetic to that, and we're going to try to work with you guys to improve your algebra skills as we teach you calculus. But if we factor this, t squared would break into t and t. And then for the 7, well, it's got to be a 7 times 1. But in order to get the minus 6 in the middle, we have to think about which of these numbers is going to be negative. And it looks like it's probably going to be that 7, and that 1's positive, right? So that definitely gives us the negative 6t. So what this means is that t is either positive 7 or negative 1. Now, because we're talking about our time always being a positive number, it seems pretty illogical that t equaling -1 is even a possibility in this question, right? Now, I don't like the fact that, hey, 7's got to be our answer, and it is, without verifying that we do change signs. But it takes like 2 seconds to like throw 7 in a number line and say, hey, what is the velocity? Which, by the way, is the derivative of position, right? At various points around 7. So let's say that we check 6 and we plug 6 into this derivative here, right, the factored version, and we get 3 times -1 times 7. Well, that's pretty clearly negative. I don't even care that it's -21. I just care that it's negative. And then if I check 8 and I get 3 times, okay, this would be +1 times +9. Well, that's 27, but I don't care that it's 27. I care that it's positive. So we definitely have a sign change. So you have just found out that 7 is your first answer, so you can cross it off. So Madison, hopefully that helps a little bit there. It's a neat little take the derivative and set equal to 0. So, all right. Anybody else have any 8.2 question? Yeah, sure, no problem. And again, we understand that a lot of you still might just be starting this. You finished up your 8.1, and that's okay. You guys, as long as once we get through this week and next week, if you are confidently up to pace by the time class starts the Monday after spring break, and you're ready to start 8.7, I think we're going to be in good shape. Okay. Maximum acceleration would be like this example that we did in 8.3. Very much so. I think so. Yeah. You would be finding the maximum value of the acceleration, which means you would probably be looking at taking the derivative of acceleration, which is kind of unusual, Madison, but I believe that is exactly what would be going on. Yeah. So, yeah, want to look at J? We can look at J. And guys, keep in mind, I'm going to set some time aside both Friday and even a little bit Monday for people that have some last minute questions on these. Okay. J. Tomorrow's agenda is only one example from the notes. So we should be able to have some time. Okay, it says for J that the position of a bug moving along the x-axis is given by x of t equal at plus b. A and b are both non-zero. Find the acceleration of the bug at any time t. This is an interesting little guy. Okay, so if we have position and we have to figure out acceleration, how many derivatives do we have to take to get there? Well, if we take one derivative of position, that gives us to velocity, right? And we have to think, okay, well, what is the derivative of at plus b with respect to t? Well, think of this. If it helps, you could kind of plug in some random numbers for a and b, like if it was 2t minus 3. The derivative of this would be 2, of course. Well, because we don't have specific numbers, we have to use the same idea and realize that, oh, the derivative is just the coefficient of the t. So a is our derivative, a constant. And that's a little worrisome, right? Because this is a Big Ten activity, right? All of our answers have to be some number between 0 and 9. But you realize 0 is one of those options. And that's what the derivative of this a is going to be, right? Hopefully, does that make sense, Emily? It's kind of a sneaky way that we had to get 0 to be an answer, and we thought this might be the most clever way. So, yep, sure. Anything else here before we call it a day? I'm going to work on the solution key for this Big Ten throughout today, tonight, and tomorrow. I hope to get it posted by the weekend at the very least. So, all right. Hey, guys, encourage your friends who, we're a little worried because, you know, we're getting about 30 to, I think we peaked at maybe 36 today. But when you talk about both Mr. Meunier's class and my class combined, that's well short of about 200 kids. But we also know that a lot of people are watching it with the recording posted to Schoology. But that recording just goes back to my YouTube channel, and I get a viewer count. And the viewer count plus the live count is well short of how many people should be watching this. And that's why we're a little worried. But you know, we're going to make sure that the people who are doing what they're doing are going to get rewarded, and the people who aren't doing what they should be doing might not be so happy with a couple of their quiz scores if they don't take them and find out that they can't drop them. So, but if you have friends that are lost, let's say that they have forgotten their Schoology password. I have a few I know that have never logged on to Schoology in the whole year because they just didn't think it was important. So they can always contact the school. There's been a message sent out where they can contact and get their Schoology password reset. Because boy, if you don't log into Schoology, I don't know how this works, right? So yeah. Yeah, Mr. Meunier says that he wants your class to have the input for the skill builder on Schoology. Yeah, if that makes sense. So he's got a skill builder input that he wants you to do. My class will do something a little different with that, but for Mr. Meunier's students, make sure you check his Schoology page so that you can do his skill builder input. So yeah, I think, Madison, we'll have some time. If I'm only going to do the one question from 8.3, we can do some more questions on this 8.2 because I think a lot of you are going to be working on it probably tonight, so or today. So yeah, we'll definitely do that during the live video. All right, kiddos. Mr. Meunier and I are going to sign out and get ready for our other classes. If you guys have any questions, you're always welcome to email us. We're pretty much on call 24/7, right? Well, maybe not in the middle of the night, right? We're not doctors, but I've been trying to answer all my email messages within 15 minutes, and hopefully I've been pretty successful. So, and then Jason, anybody else, make sure that you stop by tonight, the school, and I'll grab your Continental Math, or your, sorry, IUPUI submissions. We'll talk about Continental Math League next week. So, all right. So I will see everybody. We will see everybody tomorrow at 11 a.m. for day 4. Enjoy your Thursday, you guys, and happy e-learning, and don't forget to wash your hands. Okay. Take care, guys. We'll see ya.